Hello, hi, namaste. I, Suryadilip Sripati, welcome you all to the second amazing session of General Organic Chemistry. First of all, I would like to thank everyone for your amazing response for the first session, guys. So let's start the second session. The first question we have, if the compound is planar, select the correct statement. So here, this is an heterocyclic compound. What is an heterocyclic compound? In a cyclic ring, if there is any other atom apart from the carbon, then it is considered to be heterocyclic. Like in this compound, we have boron, which is a heteroatom. So first, let us check the hybridization with respect to the boron. It's very clear, boron is forming 3 sigma bonds. So when it is forming 3 sigma bonds, definitely it requires 3 half-filled atomic orbitals. So boron, in the first excited state, we have 1s2, 2s1, 2px1, 2py1 and 2pz0. So there is no electron in the 2p subshell. So there are 3 half-filled atomic orbitals. So it will form equal number of hybrid orbitals. So that is, it will form 3 sp2 half-filled hybrid orbitals, which can involve in covalent bond formation. Right? Now let's have a look at the each option. The boron is sp2 hybridized and the p orbital contains an unshared pair of electron. No, the p orbital does not contain any unshared pair of electron. In fact, it is empty. So the first statement is incorrect. Second one, the boron is sp2 hybridized and the hybrid orbital contains an unshared pair of electron. No, all the 3 hybrid orbitals are half-filled. So the second statement is also incorrect. Third one, the boron in sp2 hybridized state and hybrid orbital is vacant. No, even this is also a wrong statement. And the last one, boron is sp2 hybridized and the p orbital is vacant. Yes, it is sp2 hybridized and it is having vacant orbital. So definitely this is the right statement. By giving the same compound, he may ask you also to check the nature of compound, whether it is aromatic or anti-aromatic or non-aromatic compounds. Here you have an empty orbital. When you have an empty orbital with 6 pi electron system, it can easily undergo delocalization, due to which it can attain aromaticity. So this is an aromatic compound. I hope the concept is clear. Great. Let's move to the next one, guys. Identify the option in which the first intermediate is found to be more stable than the second one. Here he has given a combination of multiple intermediates and is asking us to choose the first intermediate to be more stable than the second one. Let's have a look. In the first one, you see, students, he has given a nitrogen having a lone pair which is attached to the carbon having a positive charge. Here carbon containing positive charge can be considered to be carbocation or carbonium ion. Will you consider this as carbocation or carbonium ion? What will you consider? Is carbocation and carbonium ion mean one and the same? Is every carbon containing positive charge is considered to be carbocation, or every carbon containing positive charge is considered to be carbonium ion? Let us understand. So here you have lone pair positive conjugation. Usually conjugation is always driven with pi system. Like we have pi-pi conjugation, pi positive conjugation, pi negative conjugation, pi odd electron conjugation. There are multiple types of conjugation. Apart from this, you have lone pair positive conjugation, which is a completely different kind. Here we have the same thing, lone pair positive conjugation. So once it involves in resonance, students, it will end up the resonating structure something like this. I'm sorry, students. Here the positive charge will be on the nitrogen. Yes. So here the carbon atom is getting an 8 electron system. When the carbocation gets an 8 electron system, then you consider it as carbonium ion. Any second period element or third period element, students, when it gets an 8 electron system, then we call it as onium ion, like hydronium ion, phosphonium ion, ammonium ion. Like in this case, the carbon is getting an 8 electron system due to lone pair positive conjugation. You can consider it as carbocation as well as carbonium ion. Any carbocation which can get 8 electron system can be considered as carbonium ion. Like in the second one, you see, students, it cannot get 8 electron system. So I cannot call it as carbonium ion. It is a carbocation system. It will always be a carbocation. In such case, definitely the first one is more stable than the second one. Because in the case of second one, you have total 7 alpha hydrogen system which can involve in hyperconjugation. But you know that resonance always dominates over hyperconjugation. Anyway, let's have a look at the other combinations also. In the second one, you see, you have a positive pi conjugation which can actively involve in resonance, versus another system which is 9 alpha hydrogen system, guys. This is something very important concept. Usually, always we know that resonance dominates over hyperconjugation or inductive effect. But there is one such condition, like in this case, where when you have maximum hyperconjugation and maximum inductive effect, it dominates over resonance. In such case, this one will be more stable. The first one, the first intermediate will be less stable than the second one. Is that clear? But is asking to compare first intermediate to be more stable than the second one, which already we have decoded in the first option itself. Now let's have a look at the third one. In the third one, students, if you notice, this is the bicyclo compound. What do you mean by bicyclo compound? If two rings commonly share two carbon atoms, then it is a bicyclo. If two rings commonly share one carbon atom, then it is a spiro compound. Here, what are the two carbon atoms? These are the two carbon atoms which are commonly shared. This is called as the bridgehead carbon. If a carbocation is formed at the bridgehead carbon, it will be highly unstable according to Brett's rule. When it will be stable? Only when the number of carbon atoms is greater than 8. So Brett's rule is applicable when the number of carbon atoms is less than or equal to 8. So definitely here Brett's rule is applicable. So this carbocation is unstable. On the other hand, you have 6 alpha hydrogen system which can actively involve in hyperconjugation as well as resonance. So definitely this is less stable. Got it? Now let us have a look at the last option. We have CF3 minus and CCl3 minus. If you try to compare only inductive effect, guys, definitely you will vote for CF3 minus to be more stable than CCl3 minus. No doubt. But here the negative charge is only stabilized by minus I effect, but here negative charge is stabilized by resonance, negative d orbital resonance. So definitely CCl3 minus has to be more stable than CF3 minus. So in this question, the first option is correct. Is the concept clear, guys? I hope everybody is following. If you have any difficulty, you can reach out to me, students, in the comment section, or else you can directly mail me to my mail ID, suryadilip@gmail.com. Chalo, let's move to the next one. In which of the following the second structure has more resonance energy? Resonance energy. Of course, the resonance energy is definitely applicable for the compounds which can actively involve in resonance. Greater the ability to involve in resonance, of course, it can have more resonance energy and hence greater will be the stabilization. Let us compare the first one, students, where he has given furan versus pyrrole. Both are heterocyclic compounds. Both are aromatic in nature, where oxygen having two lone pairs, one lone pair can actively involve in resonance, other lone pair will not actively involve, right? Because only any atom for involving in resonance can give only one of its orbital only, not more than one. So when you have two lone pairs only, one of them will involve. In the nitrogen, we have one lone pair which is also actively involving in resonance. This lone pair is present in p orbital. Even the lone pair on oxygen atom which is involving in resonance is also present in p orbital. Then how do you compare their resonance energy? Both are aromatic. Both are having 4 carbon atoms, 4 p orbitals of carbon and 1 p orbital of oxygen. In furan and in pyrrole, 4 carbon atoms, 4 carbon atoms with 4 different p orbitals and 1 p orbital of nitrogen. Then you can compare their ability to involve in resonance. Oxygen is more electronegative or nitrogen? Definitely nitrogen is more electronegative or less electronegative? Less electronegative. According to Pauling scale, oxygen electronegativity is 3.5 and for nitrogen it is 3. So less electronegative atom can actively involve in resonance. So definitely resonance energy for pyrrole will be high in compared to that of furan. Now let's have a look at the second one. Yes, here you have a 6 pi electron system, but it is not completely delocalized over the ring. But here you have a 6 pi electron system where it can be completely delocalized over the ring. So this gives an aromatic stability. This is an aromatic compound. Aromatic compounds with 4n plus 2 pi electron system, they have an extraordinary stability due to the ring current. So can you expect to have ring current generated? No. Ring current can be generated only when there is a circular loop. So for that, every atom has to be either sp2 or sp hybridized. But here we have an sp3. So it cannot generate ring current. So this is non-aromatic and this is aromatic compound. So aromatic compounds definitely will have greater resonance energy, right? I hope you have followed this question, guys. Chalo, let's move to the next one. Which one among the following carbocations has the longest lifespan? Longest lifespan means is asking you to compare the maximum stability. The stability has to be maximum. In the first option, we have tricyclopropyl methyl carbocation. This tricyclopropyl methyl carbocation stability stands out, students. Whenever you compare carbocation stability, as in the first question I told you, students, so it has to be first onium ion. So first will be onium ion stability. Onium ion. After onium ion, then it is additive effect. After additive, then it is scrambling. After scrambling, then we have, what is the next one after scrambling? Then we have resonance. After resonance, then we have hyperconjugation. Then we have inductive. So this is the order where you can compare the carbocation stability. So tricyclopropyl methyl carbocation is highly stable because it will have additive effect, combined effect. What is this additive effect? Let me explain you quickly, guys. This additive effect, for example, I will take the cyclopropyl methyl carbocation. This is altogether a kind of resonance. We never expect sigma electrons to involve in resonance. This is one particular example where sigma electrons can involve in resonance. What is the driving force for this? One is the bent orbitals. The sp3 hybrid orbitals are bent. The sp3 hybrid orbitals are bent. Why the sp3 hybrid orbitals are bent? Because the bond angle here is less. If the bond angle is less, why it should have bent character? Because when bond angle is less, percentage of S character is less. When the percentage of S character is less, obviously percentage of P character will be more. When the percentage of P character is more, then the bend character will be more. Once the bend character is applicable, then you have this resonance applicable. The sigma positive conjugation is applicable. Then what is this additive effect? Additive effect is a combination of bent character and electronegative nature of this carbocation. This carbocation will have which kind of effect? Minus I effect. The strong minus I effect allows the p orbitals, sp3 orbitals to involve in resonance. So there is a reason why the combination of inductive effect as well as the bent character together is called as an additive effect, which dominates than any other combinations. Like we have additive followed by scrambling, followed by resonance, followed by hyperconjugation, followed by inductive. So this one will be highly stable. Now let us have a look at the other combinations. This can actively involve in resonance. Triphenyl methyl carbocation. This is resonance stabilized. And next one is based on hyperconjugation. Next one is also hyperconjugation and inductive effect. Maximum 9 alpha hydrogen system. But this 9 alpha hydrogen system cannot dominate over additive effect. So the first one is right. Is that clear? Chalo, let's move to the next one, guys. Yes. This is a very common question, very important one. Still, I have brought into this series because the concepts has to be revised. Now, this is a cyclopentadiene has been given to you and is asking you to react with KH. Cyclopentadiene. Metal hydrides, potassium hydride. The name itself tells you hydride. Usually, any atom which will have a negative charge on it ends with IDE. For example, you have NaCl. We don't call it as sodium chlorine. We call it as sodium chloride. Magnesium oxide, potassium hydride. So already we have understood that here the hydrogen is having a negative charge. The H minus will always look out for hydrogen atom in the form of a proton. This H minus attacks this hydrogen atom where cyclopentadiene actively fires H plus ion and you get a negative charge. Thereby, cyclopentadiene carbanion is formed, which is aromatic. Along with this, hydrogen will be released. So it will form a aromatic salt. To be more specific, I can consider it as quasi-aromatic. What are quasi-aromatic compounds? Do all aromatic compounds are considered to be quasi-aromatic? No. Only when if a charge delocalization leads to aromatic stability, then only we consider it as quasi-aromatic. So every aromatic compound cannot be quasi-aromatic, but every quasi-aromatic compounds are aromatic. Yes. Clear? Along with this, he is asked to react with butyl lithium. Butyl lithium is an organometallic compound. In an organometallic compound, it will have dual character where the carbon will have covalent character as well as ionic character. Obviously, metal will be highly electropositive due to low ionization energy. Carbon, moreover, will have this negative charge, due to which this will act as a base and will pick up the H plus ion. That gives you same cyclopentadiene carbanion along with butane. So in both the cases, we are getting the common product, that is cyclopentadiene carbanion. So the negative charge gets delocalized on all the carbon atoms. So it will have how many resonating structures, guys? 5 resonating structures. Whenever you have a charge delocalized completely in the entire ring, based on the number of carbon atoms, you can consider equal to number of resonating structures. You have 5 carbon atoms, so it is 5 resonating structures. Similarly, if I take this cyclopropene carbocation, it will have how many resonating structures? 3 resonating structures, because we have 3 carbon atoms. Is that clear? So which one will be the correct combination? It will be option B. Clear, guys? Chalo, let's move to the next one. Yes, this is in this series, students, this is my favorite question, because here students do make a lot of mistake. That means they really need to follow particular strategy. For different questions, students, you need to have certain strategies. If you try to follow and answer the question with respect to that strategy, you can easily solve. So the question is, the reactivity of the following compounds with the proton, what will be the order? He has given different nitrogen containing compounds and is asking you these nitrogen containing compounds, their ability to accept H plus ion. So indirectly is asking you to check with basic character. Yes, is asking to compare with the Lewis basic character. The compound which can readily accept will be highly basic. So for that, the lone pair has to be localized and the nitrogen atom has to be less electronegative. If the lone pair is busy involving in resonance, definitely it cannot give its lone pair at the cost of resonance. So first what you need to do, you check the hybridization so that you will come into conclusion with respect to electronegativity, and then you can also compare with the localization and delocalization, which will also give you better idea to compare their basic character. So let's see, students. In the first one, you know, this is sp3 and no resonance, so this is localized. Next one is 6-membered ring, again sp3, again localized. Third one, pyrrole. Just now we have seen, students, where the lone pair is actively involving in resonance. So hybridization has to be sp2 and it has to be delocalized. Those students who really usually don't follow the concept and simply they go with the formula or the trick that number of hybrid orbitals is equal to number of sigma bonds and lone pair. So if you apply the trick here, 1, 2, 3, 4, 3 plus 1 combination, it has to be sp3. It can't be sp3. It has to be sp2. Clear? So never always go through the trick, students. Yes, if you once you know the concept, definitely when you learn the trick, you also need to know when and where to apply. So we have sp2 and delocalized. Next one, we have pyridine. Here lone pair is localized and it is sp2. In the fifth one, here it is sp3, localized, but we have an electronegative atom. So which one will be the best one, students? I think second one. How do you compare between 1 and 2? Smaller rings are relatively more electronegative. When they are more electronegative, ability to involve, to give readily, donate the lone pair will be less. So definitely we will vote for second. Second followed by first and then fifth. How did I compare 1 and fifth? Here you have an electronegative atom directly. So the minus I of oxygen will definitely decrease the electron density on the nitrogen atom in the compound 5. So the best one will be the second one followed by first one then fifth one. Out of 3 and 4, sp2, sp2, this is delocalized and that is localized. So answer is obvious. Fourth one will be the best one, followed by the third one. So the correct option will be 2. Without comparing sp2 or sp3, that is hybridization, or not considering the localization effect or delocalization effect, then it will create a lot of confusion, students. You take very good advanced books like Himanshu Pandey or MS Chauhan, you will have a lot of questions based on this. Chalo, let's move to the next one. Correct order of bond length. Yes. It's asking you to compare bond length between X, Y, Z, where you have NO2 groups. To this NO2, ortho to this we have bromine and iodine. Again to this NO2 we have iodine and methyl. Again to this we have bromine and CH3. So it's asking you to compare the bond length of X, Y, Z of these NO2 groups. How do you compare? Through SIR effect. SIR effect. Please, sir, tell me what is SIR effect? SIR effect is nothing but steric inhibition of resonance. The name itself conveys you the concept. Steric inhibition of resonance. If resonance is inhibited due to steric reasons. How resonance can be stopped due to steric reason? If the groups are so bulky that it will push the group out of the plane. When the particular orbital which has to involve in resonance, if it is pushed out of the plane, coplanarity is lost. When coplanarity is lost, there will be no resonance. Because for resonance, definitely coplanarity is must. So here, how do you compare bond length using SIR effect? In order to avoid the repulsions, greater SIR effect, what it tries to do? It tries to move away from the group. So greater the SIR effect, greater is the bond length. Yes. So in order to solve this question, I need to have a rough idea of the SIR effect. Which group which will have maximum and which group will have minimum. In this case, the SIR effect is maximum for iodine, then followed by bromine, then followed by methyl group. So this NO2, which is having both ortho groups with bromine and iodine, definitely will have maximum bond length. It tries to move away from iodine as well as bromine. Whereas in the other case, using this group NO2, this NO2, which has to overcome with iodine with methyl, and this NO2 group has to overcome the repulsion from bromine and methyl. Obviously, this NO2 will have more bond length because it will have more repulsion from iodine than methyl group. But here if you compare Z, it has to overcome the repulsion between bromine and methyl. So here the point of comparison is between iodine and bromine. Which one is giving you more SIR effect? Obviously iodine. So the maximum bond length order will be X greater than Y greater than Z. So SIR effect can also affect acidic strength. SIR effect can also affect the bond length, and SIR directly affects resonance. Is that clear? Chalo. Let's move to the next one, guys. Yes. This is the last question of today's session, students. And it is, as usual, it's a very important one. Chalo, let's have a look. Ease of hydrogen release in decreasing order. Yes, the purpose of giving you this question, students, because in this question you have almost all functional groups, all important functional groups which can have acidic behavior. Instead of taking multiple questions and highlighting their acidic character, but if I take a particular question where I can bring out all the groups which can show acidic strength, and that is the reason I have picked up this one. And as I have told you guys, and I've been telling you in the earlier session, even during my launch video also I told you, if you want me to take up any particular question, please do mail me. What is my mail ID? Yes, suryadilip@gmail.com. Chalo. Ease of hydrogen release in decreasing order. SO3H, sulfonic acid you have, carboxylic acid you have acetylene hydrogen, you have phenol as well as alcohol. What will be the acidic strength order, guys? Sulfonic acid is a strong acid. Why? Because on releasing H plus ion, it can give you equally contributing resonating structures. How many? 3 equally contributing resonating structures. Actually, resonating structures can be divided under 2 categories: equally contributing resonating structures, unequally contributing resonating structures. Equally contributing resonating structures are those which will have equal contribution for the resonance hybrid. Unequally contributing resonating structures cannot have equal contribution for the resonance hybrid. So greater the contribution, greater will be the resonance energy and greater is the stability. So sulfonate ion is sulfonic acid is highly acidic because the corresponding sulfonate ion is highly stable. Acidic strength is always compared based on the stability of the anion, and the base can be compared based on the stability of the cation, that is after accepting the H plus ion. Chalo. In this, after sulfonic acid, we have the carboxylic acid. Of course, carboxylic acid also have equally contributing resonating structures, but it is only 2 equally contributing resonating structures. So out of sulfonic acid and carboxylic acid, which one is more acidic? Yes, sulfonic acid is more acidic. Next, here we have phenol. Phenol, no doubt, it will have more resonating structures than sulfonate ion and carboxylate ion. Phenoxide ion will have more resonating structures, but even then it is less stable anion. Why phenoxide ion is less stable anion than carboxylate than sulfonate? Because phenoxide ion will have unequally contributing resonating structers. Quantity is not important, my dear friends. Quality is important. Quality is important. Like if I take some 15-20 questions and if I give you very straight away questions, then what is the point? Even if I take up 5 questions and they have to be quality based. Like similarly, here also we have better importance to quality than quantity. That is the reason why sulfonic acid, the name itself tells you it's an acid. Carboxylic acid is an acid, but phenol, we didn't give the name as an acid. Of course, it is having an acidic property. So indirectly it is conveyed that phenol is a relatively a weak acid. Okay. Now we have to compare with an alcohol and carbon containing acidic hydrogen, that too sp. Oxygen electronegativity is 3.5. sp carbon is 3.2. So which one is more electronegative? Obviously oxygen. When oxygen is more electronegative, definitely it can easily stabilize the anion. So first sulfonate, carboxylate, phenoxide, then alkoxide, and finally sp carbon. So what will be the order? For sulfonic acid we have A, then carboxylic acid we have E, AE, then we have phenol. For phenol we have C, and then we have alcohol B, and then D. So that is second option. I hope students you have enjoyed today's session. All the concepts I hope you are very clear, and for any particular question you believe that I need to give more explanation, more details, definitely you can always reach out to me. So that's all for today, students. Thank you for all your love and support. Please share and subscribe your favorite YouTube channel, Surya's World of Chemistry. Signing off, guys. Bye-bye.